Fantastic, thank you, David, and thank you. Obviously, it's great to be here. I think for the purpose of time as well, I think there's certain aspects of what I prepared here which we've maybe already covered in some context, and so I'm going to hopefully provide, I suppose, a perspective of a commercial business who is looking at bringing more sustainable technology to market, and share with you some of the thoughts of that in terms of manufacturing, but also in terms of use cases. So just to give you a quick overview for PragmatIC, we are a world leader in basically flexible integrated circuits, and we are based in the UK and basically provide foundry services to customers who want to maybe design semiconductor devices on our technology platform. But I've also brought a variety of different products to market to demonstrate the capability of that, and I'll come on to that in just a moment. But what I wanted to talk today a little bit is really in terms of the sustainability, I suppose, credentials of semiconductor manufacturing and some of the challenges and opportunities for that. And so to begin with, I kind of wanted to, I suppose, highlight some of the points in which we've already kind of touched upon. In other words, the electronics industry, a little bit of a dirty secret in some respects, the semiconductor organizations and market has basically overtaken, for example, the automotive market in terms of kind of carbon emissions. And so you can see here, Intel and TSMC, some of the largest semiconductor manufacturers, now have actually overtaken General Motors in terms of their carbon footprint and gas emissions. Also, we're looking to kind of companies like Apple, obviously in terms of consumer electronics. It's really quite I think really quite astounding that actually, in terms of Apple's kind of total carbon footprint, manufacturing equates for 74% of the carbon footprint of their business, and of which, from that 74%, over 50% is actually accounted for within the integrated circuits. And so again, this is, I think, quite a shocking view, and shows that actually much more needs to be done in terms of the impact of the semiconductor industry has in our electronic devices. So what is the root cause of this? I think we've touched upon this again already, but ultimately silicon devices, which are typically used, in mainstream semiconductor industry today, it takes a lot of energy and resources. First of all, in terms of the preparation of the silicon, it obviously requires a high purity, but also high energy to grow that crystal. But also very high energy intensive processes and tooling in order to go through a very extensive kind of processing steps, which often in some respects can take months, 6 to 9 months for complex devices. In addition, TSMC and Intel, I think, as David mentioned earlier, have had huge pressure on them to put more things in place to be reducing the amount of water consumption. With Intel wanting to be net positive in terms of water consumption, in upcoming years. And so obviously there's a lot more here which needs to be done. But at the same time, we're going to have, kind of a counterintuitive effect that actually Moore's law, which shows that actually the density of semiconductor devices is only doubling, every 2 years. Actually makes this I suppose challenge even more kind of a challenge, and that's because as we see the complexity of devices kind of increasing, and the density or the technology nodes in which you use reducing in size and heading, I suppose, now towards kind of 2 nanometers, you can see actually that requires much more increased use of volatile kind of chemicals and gases, but also an increasing use of energy, which kind of somewhat spiral out of control. And so one of the things in which one of the things in which I suppose the kind of key point in which I wanted to kind of talk about is looking at the kind of opportunity which we have to think a little bit differently about how we manufacture electronic devices. And actually, in particular, obviously we've talked already today about using alternative materials to silicon. For example, like kind of polyamide and different kind of metals, oxides, for instance. We've also talked about kind of substituting maybe different kind of parts of the tooling in the process, which doesn't require the kind of quite extreme conditions. But ultimately, I think what the opportunity is actually to design, electronics and semiconductor devices that are actually fit for purpose. rather than kind of the performance at any cost. And obviously there's a lot of innovation which is kind of driving forwards to, again, whether it's in terms of technology node and the kind of complexity of devices, but there's still a lot of use cases out there which actually don't require the same level of kind of complexity. And so actually I think there's an opportunity there, through, let's say, flexible electronics to optimize the manufacturing of that to meet, to basically have it fit for purpose rather than performance at any cost. And so that's kind of really kind of the ethos of which we have here at kind of PragmatIC. So PragmatIC semiconductor, we basically make flexible integrated circuits, and we call them flex ICs. Obviously it has a significantly lower cost rather than kinetic silicon devices, but as we'll come on to see in just a moment, we think that they're certainly more sustainable to manufacture, and there's lots of opportunity there as well. But ultimately, we think that our kind of technology or flexible integrated circuits have the the immense potential to create intelligence to everyday objects. So you can see here on the picture on the bottom left, that's effectively one of our flexible wafers. So obviously, the semiconductor market industry manufacturer typically on a 200 or 300 mil wafer. Ours is effectively based on a polyamide substrate, which makes it super thin and flexible, but also low cost. And in terms of our manufacturing capability or the kind of approach which we take, we call this flex logic, also known as kind of a fab in the box. And so you can see here, and again, what was kind of described earlier, we use a variety of kind of metal oxide, a very, I suppose, reduced kind of complexity in comparison to the silicon world. But actually this kind of allows us to significantly reduce the complexity of our manufacturing process. It allows us to remove the kind of intensive kind of process steps which are required, for those more complex devices. It allows us to reduce the footprint of our fab significantly, as you can see, but also allows us to significantly reduce the kind of cycle time rather than months or weeks. We can do it in effectively days by also increasing the automation, of our foundry. And so as a result, we currently have the capacity to manufacture tens of millions of devices per year in the UK. But with our recent investments, we are basically building a second manufacturing line in the UK, which will have excess of 1 billion devices per year, and that will only grow. But also with regards to being able to remove the certain process steps and the complexity in comparison to silicon, effectively allows us to really kind of improve the kind of sustainability credentials of our manufacturing. And so these numbers here are kind of in comparison to a typical silicon fab. We can have greater than a third of production costs. We can lower our, I suppose, CO2 footprint and the use of water by 100 times. As I said, we have a significantly faster cycle time. We have a smaller footprint, and actually, because of the automation, require far fewer people, which means overall, it's a significant kind of savings potential in comparison to silicon. But actually, when thinking about this in more detail, it's sometimes not fair, or we're not necessarily making a fair comparison here of apples to apples, because the complexity of the technology here, which we're talking about, is different in comparison to silicon. And I don't foresee that actually, flexible integrated circuits will replace silicon at all. And so actually we need to kind of think even further, and we continue to think further about how we can further drive the optimization and basically use the energy and resources that are good enough for our technology rather than kind of performance at any cost, as I mentioned previously. And so we've carried out kind of our own studies and LCAs to look at, I suppose, the hot points in terms of our kind of carbon footprint of our manufacturing line. And so we've got a variety of different initiatives which we're looking at doing moving forwards with our second kind of flex logic line kind of coming for this year. And so this is looking at the potential of capturing rainwater and treating that on site. And basically, again, having the kind of quality of our ultra pure water, which is good enough, for our processes and for our technology, again, rather than being, super kind of high quality, which is required for silicon. And And also one of the big hot points is the use of volatile organic kind of chemicals and gases within the semiconductor world. And so we hope to look at alternative VOCs, which can help reduce the quantity and an impact there, but also look at kind of on-site carbon beds, for instance, to reduce the amount of chemicals which we take off-site, because that's a huge impact, you know, to our manufacturing and the overall kind of footprint of our business. Of course, you know, we can speak a lot about, I suppose, the manufacturing, but I also want to give you a little bit of an indication of, I suppose, what is possible with this type of technology in terms of use cases and capabilities, because, you know, that helps us kind of understand and position, you know, potentially where this technology could be used and how we can become more sustainable moving forwards. So a big part of our business, you know, to prove out our technology has been around looking at ultra low cost RFID, so that's radio frequency identification, but also near field communication, NFC, as a means of, you know, demonstrating the technology. But ultimately, I think, as what was discussed earlier, to be able to identify and track items, you know, throughout their life cycle for different reasons. And I'll come into some more use case examples on that in just a moment. But actually, in the future, we're currently working on, you know, adding basic sensing capabilities, you know, to that kind of core technology platform. You know, and so this could be, you know, sensing everything from kind of temperature to strain or humidity, but also in the future, basically go into the kind of healthcare market around kind of wearable sensors at a much kind of lower cost entry point. And again, to kind of enable, let's say, capabilities to society, which, you know, previously haven't been able to access such technologies. But actually, some of the really exciting things to come is we've been working with ARM for many years now, and have recently effectively manufactured one of their Cortex M0 processors onto our technology, which basically starts to add, you know, some form of compute or intelligence, you know, actually onto a flexible substrate. As well as looking at kind of machine learning and artificial intelligence kind of circuits and processing, which again could add a form of intelligence to effectively everyday objects. And then in the future, you know, of course, we can look at imposing this type of technology with other types of technology in printed electronics, to look at things like, again, healthcare, things like displays, and basically look at, you know, opening up more possibilities in different areas. And so finally, just to kind of come on to some of the use cases that I suppose I spend a lot of my time looking at. If some of you may be aware, in terms of, certainly in the UK, the big push for becoming a more circular economy with regards to kind of plastic packaging and intelligent packaging. And so, you know, we've done a lot of work on basically looking at how we can digitize you know, and track plastic packaging throughout its life cycle by applying, you know, RFID and NFC technology to that. And so I've done, you know, lots of kind of pilots and trials with regards to basically a digital deposit return scheme, which potentially would be deployed in the UK in the upcoming years. Obviously, in the last talk, we talked about regulation and producer responsibility, but in the UK as well, we've just kind of had some updates to the Environmental Act last year, which talks about, again, making producers more responsible, you know, for their waste. And of course, yeah, improving the kind of enforcement and regulation of that. And a big part of that is effectively kind of waste tracking of different items, again, which is a, you know, huge problem throughout the world. And finally, one which I'm quite excited about, not because it involves pork, but or pigs, but actually, you know, with 30%, sorry, let me get this right, all the food which we produce globally, 30%, greater than 30% of that actually gets put into the bin, whether kind of pre or post consumer. And so we're looking at, you know, adding further supply chain traceability, using RFID and NFC, but then through some of the sensing capability, looking at how we can effectively measure the freshness of meat inside of a packet of fresh produce. And so we think that has huge potential to basically reduce, you know, millions of tons of food waste, whether that's pre-consumer or help consumers have more confidence in the food in which they're eating. And so, yeah, I just wanted to kind of inspire you a little bit, not only in terms of the credentials of the technology, but actually the possibilities of the technology in creating sustainable use cases, and obviously, I suppose, some of the potential, moving forwards for adding, even more intelligence to everyday objects. So that's it for me. If, of course, there's any questions, feel free to ask in just a moment. Thank you.